Hi there. Today I'll be presenting on absorption spectroscopy and its uses in determining the electronic structure of cyanide dye molecules and a comparison of the experimental results with molecular models and computational methods. So the research goals of this experiment were to determine how absorbance changes as a function of conjugated chain length in cyanide dyes, particularly these four cyanide dyes studied here. The goals were also to assess the accuracy of different molecular models in predicting the size of the homological gaps of these four dyes, in particular, the particle in the box model, the Huckel molecular orbital model, and the Hartree-Fock approximation and the NDDO models. But why do we even care if these methods are accurate? Well, the HMO model and Hartree-Fock models are commonly used in physical chemistry, and they're essential to computational chemistry, so we actually care if these things are doing a good job, if they're accurate, when we're doing our further analyses and applications. So what do we think is going to happen in this experiment? My hypotheses are that the wavelength of maximum absorption will increase with increasing length of the hydrocarbon chain between the cyanide moieties. So essentially, as the size of the conjugated region of the molecule increases, the energy gap will decrease. I also hypothesize that the Hartree-Fock, so the NNDO methods, so the MNDO method and its improvements will most accurately predict the HOMO-LUMO gaps of the dyes. These models are the most refined and expanded. For example, they account for the intermolecular force interactions between molecules, which can impact the HOMO-LUMO gaps. So what was the experiment that we actually did? What were our methods? So in this experiment, we did absorption spectroscopy in which a source of light, the light traveled through biconvex lenses and was focused onto the sample here in a cuvette. The sample was at the focal point of the light. It absorbed some of the light, and then the rest of the light traveled from this reflecting mirror and then into the detector through another focusing lens. Essentially, how the UV vis system worked is that you had a source. In our case, it was a UV LED, an incandescent bulb. The light shined on the cuvette with the dye in it. The dye absorbed some of the light. The light that was not absorbed reached the detector, and the detector spit out a spectrum in which we can analyze for the wavelength of maximum absorption. In this experiment, we ran blanks before every run with methanol, and then slowly added drops of dye before taking the final spectrum here when it reached a high enough absorbance. For each dye, we collected a spectrum and got the wavelength of maximum absorption. Generally, we saw the trend that we expected to see, that the wavelength would increase with increasing length of the distance between the cyanide moieties in the dye. So how do these results here, these wavelengths that we measured, compare to the theoretical models that we're thinking about? So the first model is the simplest model. It's a particle in the box model, where essentially an electron is trapped in an infinitely tall potential well, and the energy is described by this equation here, where N is the energy level number, H is Planck constant, M is the mass of an electron, and L is the length of the box. In this case, that's the length of the conjugated section of the molecule. So we calculated the energy gap between the HOMO and the LUMO. So essentially this N here is number of pi electrons over 2, and then N2 is N1 plus 1, where then the length was calculated with bond length. And from this energy, we could calculate wavelength, which is what we got for all of the molecules. And to compare that to experimental wavelength, there were percent errors ranging from 1 to 20%. So it was pretty good for dye 4, but not very good for dye 1, with an average error of about 9.9%. And then moving on to the Huckel molecular orbital model. So it's essentially a very specific case of a molecular orbital model, essentially transforming the Schrodinger equation in this equation here, where this is the coefficient on the orbitals, and you can use an n by n secular determinant to find the energy of molecular orbitals. So from a secular determinant, it looks something like this. But here we actually use the Huckel approximation, which assumes that this term is equal to 0, and that you can ignore the H term, unless it is for adjacent atoms, and that for adjacent atoms equal to beta for carbon, but it's equal to 0.8 times beta for nitrogen, where K is equal to 0.8, which is a constant that corrects for atoms that are not carbon. And then for on the same atom is equal to alpha for carbon and equal to alpha plus H beta, for H is equal to 1.5 nitrogen, and beta is a unit of energy. You're able to then use all of this to sort of turn this scary secular determinant into something that looks more like this, where X is equal to alpha minus E beta, and then you can evaluate the matrix to find an expression where you can solve for X, which is what we did in Mathematica for all of the dyes, where the values of X times beta are equal to the energy of the orbitals in the molecule. So looking at only the pi electrons, we fill up each of these energy diagrams that we made for each of the dyes. In this case, it's for dye 1. So there's 6 pi electrons in dye 1. And you see that the energy gap is right here. So this difference here is delta coefficient, which we calculated for each. And then the delta coefficient times this literature value of beta is equal to the energy gap, and that energy gap can be used to find the wavelength. And so to compare the predicted wavelength to the experimented wavelength, there were percent errors from 3 to 13%. So overall, they were generally lower than they were for particle in box, with an average of about 9.7%. And then finally, the last sort of calculations we did with the Hartree-Fock, using the Hartree-Fock approximation, essentially use molecular modeling, several empirical methods based on the Hartree-Fock approximation and the NDDO models. So to find energy, you would have to use the Schrodinger equation with the Hamiltonian. But the last term of the Hamiltonian is this electrostatic potential energy. And this is very hard to solve for, because when you have a multi-electron system, you end up with a whole bunch of multi-electron integrals, which are really hard to solve for. So instead, in the Hartree-Fock approximation, it approximates this electron-electron repulsion with an electron interacting with an average electrostatic field of all of the rest of the electrons in the atom. But the Hartree-Fock is a nonlinear integral differential equation. So it's actually very difficult to solve analytically. So instead we use molecular modeling with Cygress, where molecular model packs, MOS, MPO, AM1, RM1, and PM3 were used. AM1, RM1, PM3 are all improvements on MNDO. These different models each have their own benefits and drawbacks. So MNDO, its parameters are defined by a limited data set, and it tends to have problems with short range interactions and doesn't describe hydrogen bonding very well. while AM1 alleviates those problems with short-range interactions and more accurately describes hydrogen bonding in MNDO. PM3 is a reparameterization of AM1 that uses less Gaussian functions to describe it, and RM1 is also an reparameterization of AM1, but it uses a more complete training data set. And that means it probably should produce more accurate data because it has that more of a basis. Now, to look at what we actually were able to calculate from the energies from this molecular modeling, the wavelengths in general were larger than they were for the experimental wavelengths, and the errors were as big as 22%, but as low as 0.69%. On average, the errors were lowest for the AM1 and the RM1. And as you can see, you have the lowest error in the RM1 here. You can generally expect that RM1 would be better than the other ones, and also that MNDO would be the worst. So we can say that out of these, AM1 and RM1 do the best job. Additionally, these calculations with Cygress were fairly easy to do once figuring out Cygress works, a lot easier than manually doing calculations. So some more conclusions on this, besides the fact that we sort of figured out that our hypothesis that the Hartree-Fock and NDO modeling would do the best job, and that RM1 of those would do the best job because it has the largest training data set. There's more to think about. So some things to draw on is that we could do this whole entire experiment a lot better by decomplicating the spectroscopy setup. So spectroscopy, as I explained, really only needs to get the light to the sample and then get the light that is not absorbed by the sample to the detector. It doesn't need to be bounced back and forth through these lenses and mirrors. Additionally, we could expand on our research by doing a similar line where we determine the energy gap of fluorescent molecules with fluorescence. We could also think about how there are some limitations to the Huckel model. So if we wanted to do more stuff with different molecules, we couldn't look at non-planar systems. It has to be limited to planar systems or nearly planar systems. There are also limitations to the NNDO modeling systems that we use. Since Hartree-Fock is a mean field theory, effects due to dynamical electron correlation are not described well, so that's a limitation to it. But a big limitation to our experiments would be that since the parameters are determined by fitting to a collections of empirical data, and MNDO is only based on 100 points, PM3 is only based on 800 points of data, they are only good at describing common elements like hydrogen, carbon, nitrogen, oxygen. There's not enough data in their parameter sets, or what describes the parameters, to actually calculate those. So to have a broader range of applicability, you would have to use data sets like PM6 or PM7 that are parameterized for 70 elements and thus have a lot more applications. So going forward, if we wanted to do more work, we might want to think about testing things with PM6 or PM7. We could even apply these methods in the real world to predict the wavelength of absorption of a theoretical product, such as maybe a chemist is working on a synthesis for a dye, and they haven't made it yet, but they're like, I'm looking at the synthetic process to make this molecule. What color would this molecule be? And they could use these methods to calculate it. That's all I had, but thank you for your time. Have a wonderful day.